This is M.W. Penn, and Sam and I are here to talk about adding and subtracting fractions. The slides of this presentation are courtesy of MathWord Press. We know that a fraction is a number. Fractions answer the same question all number answers. How many do you have? Here we have a unit divided into two equal parts. If we have one of those parts, we have 1/2 of the unit. Another unit is divided into three equal parts. These are thirds, and if we have one of them, we have 1/3 of the unit. We see another unit divided into four equal parts. If we have three of those four equal parts, we have 3/4 of the unit. That's how many we have. When we look at a fraction, we see that it is composed of two different parts. There is a number at the bottom and a number at the top. The number at the bottom is called the denominator, and it tells us the number of equal parts dividing a whole. The numerator is the number on top, and it tells us how many of these equal parts we have. Looking at the fractions on this slide, we see that we have 1/2, or one of two equal parts, 1/3, or one of three equal parts, and 2/5, or two of five equal parts. We also see another fraction, 5/4. 5/4 tells us that a unit has been divided into four equal parts, and we have 5 of them. That's really not so difficult to understand. Suppose we made a platter of sandwiches for a luncheon with friends, and we cut each sandwich into 4 equal parts, or fourths. Well, if Bear were one of our friends, he might eat 5 of those parts. Goodness, Bear might eat 6 of them. But if he ate 5 of those 1/4 sized parts, he would eat 5/4. Let's look at the number at the bottom of a fraction, the denominator. The denominator tells us how many equal parts divide a unit. And what happens when the denominator increases? When the denominator increases, it means that the unit is divided into more equal parts. And if we divide a unit into more parts, these parts have to be smaller. Here we see the denominator increase from 2 to 4 to 8. And what happens as the number at the bottom gets larger? The pieces increase in number, but they are smaller. The unit is divided into more and more, smaller and smaller equal parts. Now let's look at this number at the top of the fraction, the numerator. The numerator tells us how many of the equal parts we have. Here we're looking at a unit divided into fourths, and we have 1 of them, 2 of them, 3 of them, 4 of them, and even 5 of them. We see that when the numerator increases, we have more and more of the same size parts. Now let's add and subtract fractions to find out how many we have. Adding or subtracting fractions with the same denominator is really just a matter of counting up how many we have. If we have 2/3 and add 5/3, we add up the number of thirds we have. We have 7/3. 4/5 plus 2/5 means that we have 6/5. 4/4 minus 1/4 simply means that we have 3/4 remaining. So adding or subtracting fractions with the same denominator is just a matter of adding or subtracting the numerators to find out how many we have. Because fractions are numbers, we can locate fractions on the number line. Here we see a unit divided into 3 equal parts, or thirds, and 4 equal parts, or fourths. And there are many things we can learn from looking at these numbers on the number line. We know that a number to the right of any other number on the number line is the larger number. So here we can see that 1/3 is a larger number than 1/4. Well, that makes sense. If we divide a unit into 3 equal parts, they will be larger than if we divide a unit into 4 equal parts. And we also see something else interesting on the number line. We see that 3/3 is equal to a unit, and 4/4 is also equal to a unit. 3/3 and 4/4, therefore, are equal to each other. They're equivalent fractions, and they both equal 1. It's also easy to see addition or subtraction of fractions on the number line. In this slide, we found a segment the length of 2/3 and added to it a segment the length of 3/3. This performed the addition of 2/3 plus 3/3 and arrived at the sum of 5/3. At the bottom, we began with the segment the length of 6/3. We then counted back a unit of 2/3, performing the subtraction 6/3 minus 2/3, and found that the result was 4/3. Now let's practice adding and subtracting fractions that have the same numerator, which is really just counting up how many we have. 1/2 plus 3/2 equals 4/2. 2/7 plus 4/7 means that we do have 6/7. 1/3 plus 2/3 plus 5/3, we have 8/3. And 5/5 minus 3/5 leaves us with only 2/5. This is really easy. Just add or subtract the numerators. But what if we're trying to add or subtract fractions that have different denominators? What would be the simplest way to do that? Can we add 1/2 to 3/5? Or can we subtract 3/7 from 2/3? The easiest way is to make the denominators the same. Once the fractions share denominators, addition and subtraction becomes easy. So can we make the denominators the same? Can we have the fractions share a common denominator? Here, we're trying to add 1/2 and 3/5, fractions that have different denominators. Is there a way to make the denominators of these fractions the same? Actually, we can do that, and it's pretty easy, because you see 1/2 is really equal to 5/10. And 3/5 is equal to 6/10. Well, we can add 5/10 and 6/10 quite easily. In fact, our friend Square Bear could probably do that. He would just count them up and find that he had 11/10. So let's take a look at how we can do this. To change the denominator of a fraction without changing the value of the fraction, you just have to know a few simple things. The first is that fractions can be written differently and still name the same quantity. That's because we can divide a unit into equal parts in many different ways. Look at the unit at the bottom of this slide. It has been divided into 2 equal parts, 3 equal parts, and even 6 equal parts. But it did not change the value of the unit. It is still 1 unit. Bear might say, "I don't care how you cut the cake. If you give me all the pieces, I still have all the cake." We know that two numbers are equivalent if they occupy the same point on the number line. So let's look at this number line. We've divided it into 2 equal parts, or halves, 3 equal parts, or thirds, 4 equal parts, or fourths, 5 equal parts, fifths, 6 equal parts, or sixths. If we have one of 2 equal parts, we have 1/2 of the unit. But what if we have 2 of 4 equal parts? We still have half the unit. How about 3/6? If we have 3 of 6 equal parts, we have 1/2 of the unit. The same is true of 1/3 and 2/6. If we have 2 of 6 equal parts, we have 1/3 of the unit. That means that 1/3 and 2/6 are equivalent fractions. They name the same quantity. And here at the end of the number line, where we have marked off 1 unit, we see that if we have 2 halves, 3/3, 4/4, 5/5, or 6/6, we do have a unit. 2 of 2 equal parts is equal to 1. That's very important to remember. And that's the second important thing that you have to know. That is the 2 halves, 3/3, 4/4, 6/6, 20/20. Mathematicians would call this n over n. Well, they all equal 1. Look at these area models at the bottom of the slide. We see that 2 halves do cover an entire unit, as do 4/4 and 5/5. Remember what Bear said, "No matter how you cut the cake, if you give me all the pieces, I still have all the cake." But now that we know that each of these fractions is equal to 1, we've learned something very important. What happens when you multiply something by 1? 2 times 1 is 2. 4 times 1 is 4. 9 times 1 is 9. And 1047 times 1 is 1047. 1/3 times 1 is 1/3, and 2/7 times 1 is 2/7. In fact, if you multiply any number by 1, you don't change the value of that number. That's why we call 1 the multiplicative identity. Multiplicative identity is a pretty big term, but all it means is that if you multiply any number by 1, you do not change the value of that number. Let's see what happens to a simple number, 1/2, when we multiply it by 1, but in the form of 2 halves. We know that 2 halves equal 1, and when we multiply 1/2 times 2 halves, the result is 2/4. But look at 2/4 and 1/2 on the number line. They name the same quantity. They are equivalent. They're equivalent fractions. Let's multiply 1/2 by 1 in the form of 3/3. 1/2 times 3/3 equals 3/6. That means that if we divide a unit into 6 equal parts, we have 3 of them. And look at where 3/6 is on the number line. 3 of 6 is the same as 1 of 2. 3/6 equals 1/2. Let's multiply 1/2 by 5/5. 1/2 times 5/5 equals 5/10. But look at 5/10 on the number line. It is another way of writing 1/2. It means that we've divided a unit into 10 equal parts, and we have 5 of them. 5/10 is equivalent to 1/2. Suppose we wanted to find an equivalent fraction for 1/3, but a fraction that had the denominator of 9. Well, we know that 9 divided by 3 is equal to 3. So if we multiplied 1/3 by 1 in the form of 3/3, we would get a fraction equivalent to 1/3, but with a denominator of 9. 1/3 times 3/3 equals 3/9, a fraction equivalent to 1/3, but with the denominator of 9. Let's find a fraction equivalent to 3/8, but with a denominator of 16. 16 divided by 8 is 2, so if we multiply 8 by 2, we will get the number 16. So let's multiply 3/8 by 1 in the form of 2 halves. 3/8 times 2 halves equals 6/16. This is a fraction equivalent to 3/8, but with the denominator of 16. We'll do the same for 5/9, looking for a fraction with a denominator of 27 that is equivalent to 5/9. If we multiply 5/9 by 1 in the form of 3/3, we find that the product is 15/27. 15/27 is a fraction equivalent to 5/9, but with a denominator of 27. If we wanted to find a fraction equivalent to 2/11, but with the denominator of 55, well, we would just multiply it by 1 in the form of 5/5. And that would give us an equivalent fraction with the denominator of 55. One thing you should have noticed when we were looking at the number line, and that is that equivalent fractions have denominators that share factors. For example, the denominators of fractions equivalent to 1/3 will always have 3 as a factor. The denominators of fractions equivalent to 1/5 will always have 5 as a factor. The denominators of fractions equivalent to 1/7 will always have 7 as a factor. The denominators of fractions equivalent to 1/9 will always have 9 as a factor. And think about this. If these fractions with a denominator of 9 have 9 as a factor, well, they will also have 3 as a factor, because 3 is a factor of 9. You know a lot about factors because you've been studying multiplication. But this is something important to think about. Equivalent fractions have denominators that share factors. Let's look at some equivalent fractions on the number line, realizing that if numbers occupy the same point on the line, they name the same quantity. Let's first look at fractions that are equivalent to 1/2, or 1 out of 2 equal parts. What are some fractions that are equivalent to 1/2? 2/4, 3/6, 4/8, 5/10, goodness, even 10/20. If we divided a unit into 20 equal parts and we had 10 of them, we would have 1/2 of the unit. And notice the denominators of all these equivalent fractions. They have 2 as a factor. Let's look at fractions equivalent to 1/3, 2/6, 3/9, 4/12, 5/15. All of these denominators have 3 as a factor. And how about 1/5, 2/10, 3/15, 4/20, even 5/25? All of these fractions do have 5 as a factor of the denominator. And look at some of these other interesting characteristics. How about 3/15 and 5/15? 3/15 is equivalent to 1/5, and 5/15 is equivalent to 1/3. But look at that denominator, 15. It has factors of both 3 and 5. So it could serve as a denominator for equivalent fractions for both 1/5 and 1/3. The important thing to remember is that equivalent fractions have denominators that share factors. So we've already learned quite a few things. First is that if we want to add 2 fractions with different denominators, we should find fractions equivalent to the fractions we want to add, and that these fractions should have the same denominator. And now we know that these fractions will have denominators that share factors. In other words, fractions that could be equivalent to both 1/2 and 1/5 could have 10 as a common denominator, because 10 has both 2 and 5 as factors. Suppose we wanted to add 1/3 and 1/4. We should find a common denominator that has both 3 and 4 as factors. In other words, 12 could serve as a common denominator for both thirds and fourths. How about fractions equivalent to 1/4 and 1/5? Well, they could share a common denominator of 20, because 4 and 5 are factors of 20. If we wanted to add 1/3 and 1/5, we could find a common denominator for equivalent fractions that have both 3 and 5 as factors, and 15 would serve as a common denominator. How about fractions equivalent to 1/2 and 1/7? Well, they could have 14 as a denominator because 14 shares factors of both 2 and 7. But what if we multiplied the denominators of the fractions we're trying to add together? If we multiply the denominators of the fractions together, the product will have both denominators as factors. Let's look at the simple addition problem of 2/3 plus 1/5. How do we add thirds and fifths? Well, we should find equivalent fractions for both 2/3 and 1/5. Equivalent fractions that share the same denominator. What denominator would suit both thirds and fifths? Well, if we multiply 3 and 5 together, we find that 15 could serve as a denominator for equivalent fractions for both thirds and fifths. If we multiply 2/3 by 1 in the form of 5/5, we find a fraction equivalent to 2/3, but that has 15 as a denominator. If we multiply 1/5 by 1 in the form of 3/3, we will find an equivalent fraction with 15 as a denominator. 2/3 is equivalent to 10/15, and 1/5 is equivalent to 3/15. We can easily add 10/15 to 3/15. That problem is so simple that even Bear could do it. 10/15 plus 3/15 equals 13/15. So when we want to add two fractions that have different denominators, we only have to find equivalent fractions for these fractions, but equivalent fractions that share a common denominator. To do this, we can multiply the fractions by n over n, where n is the denominator of the other fraction. Let's add 2/3 and 3/7. When we multiply 3 and 7, we see that a possible common denominator is 21. It has both 3 and 7 as factors. So how do we convert 2/3 into an equivalent fraction with the denominator of 21? We simply multiply 2/3 by 1 in the form of 7/7. The equivalent fraction is 14/21. Now we'll multiply 3/7 by 1 in the form of 3/3. We find an equivalent fraction for 3/7 of 9/21. It's simple to add 14/21 and 9/21. We just count up how many 21sts we have, and we'll let Bear do that. Suppose we want to add 2/5 and 5/8. Well, we'll multiply 2/5 by 1 in the form of 8/8, and we'll find an equivalent fraction, 16/40. Next, we'll multiply 5/8 by 1 in the form of 5/5, and find an equivalent fraction of 25/40. Now we just have to add 40ths to find out how many we have. Suppose we want to subtract 1/2 from 5/9. Multiplying 9 and 2 together, we find that a common denominator could be 18. we'll multiply 5/9 by 1 in the form of 2 halves, and find the equivalent fraction, 10/18. Now we'll multiply 1/2 by 1 in the form of 9/9, and find an equivalent fraction of 9/18. How do we subtract 9/18 from 10/18? We just subtract the numerators to find out how many 18ths we have. Let's try one more. 5/6 plus 1/5. We multiply 5/6 by 5/5, and we find an equivalent fraction of 25/30. Then we multiply 1/5 by 6/6, and find an equivalent fraction of 6/30. So we're adding 25/30 to 6/30. This really is quite simple. Bear got the answers of 23/21, 41/40, 1/18, and 31/30. Good job, Bear. But let's look at something else. Suppose we wanted to add 5/6 and 1/12. Using our simple method, we would multiply 5/6 by 12/12, and we would find the equivalent fraction of 60/72. When we multiplied 1/12 by 1 in the form of 6/6, we would find an equivalent fraction of 6/72. And when we let Bear add them together, the answer would be 66/72. But look at this 6 and this 12. These denominators already share a common factor. After all, 6 is a factor of 12. Suppose we multiplied 5/6 by 1 in the form of 2 halves. That would give us the equivalent fraction of 10/12. We could then add 10/12 and 1/12, and our answer, the sum, would be 11/12. So did we actually get two different answers? Not at all. 66/72 is an equivalent fraction for 11/12. The calculations may seem a little more difficult when we're adding 70 but this method always works. We can always use the method of multiplying each fraction by n over n, where n is the denominator of the other fraction. It will always give us the right answer. Because 6 is a factor of 12, we could see that in the last addition, 12 could serve as a common denominator. But so could 24 and 48. They're all common multiples of 6 and 12. If we used different denominators and found what we thought might look like different answers, what would we see if we viewed them on the number line? Well, we'd see that they all occupy the same point on the number line because they are all equivalent fractions. They're all equivalent to 11/12. So one more time. To add fractions with different denominators, we find equivalent fractions that share a common denominator. The easiest way to do this is to multiply each of the fractions by 1 in the form of n over n, using the denominator of the other fraction 4n. If we were going to add 2/3 and 1/5, we would multiply 2/3 by 5/5, and we would multiply 1/5 by 3/3. We would find equivalent fractions that share the denominator 15. And if we don't feel like adding numerators, we can let Bear do that. You may have noticed that when I multiply fractions, I don't pay much attention to the order. Here I've multiplied 5/6 by 2 halves. Or have I multiplied 2 halves by 5/6? It really doesn't matter because of something called the commutative property for multiplication. I've used it so long, I don't even think about it. And you should learn to use it often, too. It's so important that I once wrote a poem about it. 7 plus 4 and 4 plus 7 always add up to 11. 2 times 6 and 6 times 2 both equal 12. It's always true. When we add or multiply, the order doesn't signify. The numbers aren't position bound. They can commute or move around. That's why they call it the commutative property. And here's the secret. It's a fact. They cannot move when you subtract. Don't you just love math? I always love teaching math. It's such fun. This is M.W. Penn, and Sam and I hope that you'll enjoy math as much as we do.